Hi everyone, in this lecture I'm going to go over the last part of chapter 16, which is about hash tables and hash sets in Java. So in Java library, sets are implemented as either hash sets or tree sets. Later in this course we will talk about tree sets and how tree structure works, but in this lecture we're going to focus on hash sets and hash tables. Hashing is the action of placing items into an array at an index determined from the element. So the index in which every element is stored in an array is determined by the value of that element. A hash code is an integer value that is given to an object of a class or to an element, and it is computed using the value of that object. This value, this integer value, which we call it a hash code, is calculated in a way that different objects are likely to yield different hash codes. So if you want to calculate the hash code of two different objects, with a high likelihood they should result in different hash codes. Then we have a concept of collision in which two or more distinct objects would have the same hash code. So it means that they should all be stored in the same element in an array, or in the same index of an array. That's why we say collision has happened, which means they all want to be in the same index of an array. A good hash function minimizes the number of collisions, but if a collision happened in a hash table, then there should be some mechanism to resolve that collision. A hash table uses the hash codes to determine where to store each element. In fact, the hash code would be either the same as the index of the array that we store the element, or the hash code should be manipulated and then becomes the index of the element in the index of the array in which we store that element. So next we're gonna take a look at an example of hash code values for objects of class string. In Java, for different for different objects of class string like Adam, Eve, Harry, Jim, Joe, and these strings, we compute an integer value which we call it a hash code. So the hash code of Adam is this 7-digit long integer, or the hash code of Jim is this 5-digit long integer. So as you see, different strings have different hash codes. Now that we have defined the hash codes, let's see a very simplistic implementation of hash tables in Java. Let's assume that we are going to implement a hash table using an array that stores the elements in a set, and basically the hash code that we have for the objects is used as an array index into the hash table. So basically we assume that the hash table is a very large array, and it has many indices. In fact, for every hash code, this array has one index. So what we do is we store every object at its hash code location. So if for example Jim's hash code is 74478, we store Jim in the array with index in the array's element or in the array's cell with index 74,478. So this is very simple to look. This is a very simplistic implementation, and it's very simple to locate an element in this huge array. All we need to do is, for example, if you're looking for Eve, you can find its hash code, and that hash code would be the index of the cell in which Eve is located in, or Eve is stored in. So you can very simply find the location of every string that you want, but the problem is it's not practical because you cannot create this huge array in Java, or if you create this huge array in Java, then it would be very costly because you're wasting a lot of resources, a lot of memory to create such huge array. A more realistic hash table is a more realistic implementation of the hash table is to assume that we have a reasonable size array, and let's assume that the size of the array is array length. So whenever you have a hash code for an element like x, you call that hash code h, and if h is negative, you negate it, so you make all the hash codes positive. Basically, we get the absolute value of the hash codes to make all of them positive, and then we use the remainder operation to decrease the hash codes that are greater than the array length to make them less than array length. For example, if the array length is 100, so with this operation of finding the remainder of h when it's divided by array length 100, we are converting all the hash codes from to a number from 0 to 99, because the remainder of division of any number when it's divided by 100 would be a number from 0 to 99. So the remainder of a number is either 0, 1, 2, 3, all the way to 99 when it's divided by 100. So that's why when you find the remainder of the hash code, you get the position or the index in which you need to store that object. So x should be stored in position, in index position, where position is equal to the hash code of x mod array length, which means remainder of h when it's divided by array length. So when you do this, then there would be a small problem. The problem is you may have collision. So you may have two different elements or two different objects that are mapped into the same, that are stored in the same array cell. If this happens, if collision happens, we need to handle collision. So what's the strategy to handle collision? A simple strategy can be separate chaining. What does it mean? It means that all colliding elements in a hash table should be collected in a linked list of elements with the same position value. What does it mean? It means that every cell of that hash table should store a linked list of elements whose position are the same in the table, in the hash table. So we call these linked list buckets. So if two or more elements in a hash table collide, which means they are mapped to the same cell of the array, we should put them in the same bucket, which means we should store them in the same linked list. Each entry of the hash table points to a sequence of nodes containing elements with the same hash code. Not the same hash code, with the same hash code remainder, which means their hash codes, remainder of their hash codes, if it's divided by array length, should be the same. Sometimes we call h remainder of h as the hash code of that element. So instead of saying that h is the hash code, we say position is the hash code. So there are different definitions, but you understand the concept. When you want to have a reasonable size array, you need to divide the hash code by a number and find the remainder, and that remainder would be the position of that element in the hash table with a reasonable size. It's important to know that a hash table can be implemented as an array of buckets. So the way that we implemented it was an array of buckets. So a hash table, it's not a weird it's not a weird data structure. It's an array, and we all know what arrays are. But it's an array of buckets, and each bucket is a sequence of nodes that hold elements with the same hash code. So every bucket can be implemented by a data structure like a linked list, which can store a sequence of nodes. So here is an example of a hash table. As you see, it has many cells, and each cell points to a linked list. So for example, Juliet, Catherine, and Tony, they all have the same hash code 79. Adam has hash code 77, Sarah has hash code 76, Eve has hash code 75, Larry 74, and Sue and Harry, they both have the same hash code 65. So in the implementation that we proposed for a hash table, which was an array of buckets and every bucket was a linked list, can be a very powerful data structure. In the rest of this lecture, we're going to see different operations on this data structure. First, we want to find out how to search for an element in this data structure. So we want to see how finding an element looks like in this hash table. First of all, let's assume that you're looking for an element called obj. So object obj refers to the element that we are looking for, or contains the element that we are looking for. To find that element, we have to compute the hash code of that element and compress the hash code by dividing it by the size of the hash table that we have. So when you calculate the hash code and you compress it, it gives you the index h into the hash table, and that index would be the only index in which object obj can be stored. So if the object cannot be found in that index or in that bucket, it means that it doesn't exist in the whole hash table. So we focus on searching through that bucket and see whether that element is in that bucket or not. So what we need to do is we need to iterate through the elements of the bucket at position h. As I said, the bucket can be implemented by linked list, so we can iterate through the linked list by creating an iterator. We have discussed how to iterate over a linked list before. We check to see if there is an element in that linked list equal to the object that we are looking for. If you find a match in that bucket, then we say the object is found in the linked list in the hash table. Otherwise, we say we couldn't find the object in the hash table. So if there are no or only a few collisions in the whole hash table, it means that the length of the linked lists that are existing in each bucket of that hash table are very, very short, or either you have a linked list of size 1, 2, 3, or a very short linked list in each bucket, and therefore if the number of collisions are small if you have very few collisions, it means that locating elements in the hash table is very inexpensive, and you can take a constant time to find an element in a hash table. We will see later that if you want to add or remove an element to or from a hash table, if you have very few collisions, then it would be very inexpensive to add or remove elements to or from a linked list too. So what I'm saying is we need to have a good hash tables, we need to have a good hash code so that we can minimize the number of collisions in our table. So next, let's talk about the two important operations in a data structure, which is adding an element or removing an element from a hash table. So let's first talk about the algorithm to add an element to a hash table. The first thing we need to do is to compute the compressed hash code, which means that calculate the hash code and find the remainder of the hash code h when it's divided by the length of the bucket list or the array list containing buckets. Then the next step is to iterate through the elements of the bucket at position h, because we know that the element that we're going to add should be placed in the bucket at position h because its compressed hash code is h. You cannot place it in any other bucket. And then for each element in the bucket, we should check whether it is equal to the object, because we are creating a hash set. So we don't want one element to be placed in a hash table twice. Basically, we don't like repetitions in a set. Repetition in a set is not allowed. It means that if you want to add an element in a set, you have to first check whether it exists in the set already or not. If it exists, you have to do nothing. So after finding the position h and after finding the position h, you have to check all the elements in that bucket and see whether they're equal to the object that you want to add. If a match is found among the elements of that bucket, it means that that object is already part of the set, so you need to exit and do nothing. Otherwise, you need to add a node containing that object that you want to add to the beginning of the node sequence. So you need to add that object at the first of the linked list existing in the bucket with index h. If the load factor exceeds a fixed threshold, you need to reallocate the table. What does load factor means? Load factor is equal to the number of elements in the hash table divided by the number of buckets in the hash table. That gives you a number which we call a load factor. The load factor should not exceed some value. If it exceeds some value, it means that the hash table is getting crowded and the linked list in each bucket is growing and they become longer and longer and then that means that the operations that we're going to do on hash tables, like searching for an element or adding an element or removing an element, are getting costlier and costlier. So we need to reallocate the table, which means that we need to create another table with twice the number of buckets and reallocate all the elements in the old reallocate means we need to transfer all the elements from the old table to a new table with twice the number of buckets as the older one. This way we can reduce the load factor. Why? Because load factor equals the number of elements in a hash table divided by the number of buckets. So when you double the number of buckets, you're halving the load factor. You are dividing the load factor by 2. and this way you're not allowing the load factor to exceed a fixed threshold. So again, as I said, the load factor measures how full the table is, which is and then load factor is calculated by the number of elements in the table divided by the table length, which is the number of buckets in the table. If you do reallocation when the load factor is exceeding a fixed threshold, the operation of adding an element would still be constant, but sometimes it's gonna exceed the constant value. That's why we write it as O1 plus. O1 means constant value. O1 plus means sometimes it may exceed the constant value and it becomes costly, but in average, adding an element to a hash table would have a constant cost. So next, let's talk about removing an element from a hash table. It's similar to adding it, but you have to take a closer look to understand the difference between adding or removing an element from a hash table. First, you need to do the same step, which means computing the hash code to find the bucket that should contain the object that we are going to remove. And then in the second step, you have to try to find that element by going through all the elements of that bucket with the index equal to the hash code of the element that you want to remove. And then if you find that element, you need to remove it, and otherwise you have to do nothing and exit from the algorithm, from the operation. And then it is important to shrink the table if it becomes too sparse. What does sparse mean? It means that if the load factor falls behind some load threshold, then you need to simply shrink the table, which means that you have to reduce the number of buckets in that table. One way of shrinking the table is to divide the number of buckets in half and reallocate the elements of the table by transferring them from the old large table to the smaller new table with fewer buckets. If you think about the the efficiency of removing an element from a hash table, we will come up with the same complexity with the same cost, which is O1 plus. O1 means the cost is constant. There's a plus here, which means that sometimes we need to reallocate the elements of a table if the table becomes too sparse. That will add some cost to the operation, but in average the operation of removing an element from a hash table would be constant. So generally speaking, and if you want to consider the average value of the cost of removing an element from a hash table, you can say that the operation of removing an element takes a constant time, and it's a very inexpensive operation. Next, we talk about how to iterate over a hash table. In order to iterate over a hash table and see all the elements stored in the hash table, we need to go over all the elements in every bucket. So if the iterator points to the middle of a node chain, middle of a bucket, then it's easy to get the next element. It would be very similar to what we have done in linked list, and just finding the next element in the linked list. If the iterator is at the end of a node chain, at the end of a linked list, then you need to skip over the empty buckets and find the next non-empty bucket in that list of buckets in the hash table. And then we need to advance the iterator to the first node of the first non-empty bucket when we find a non-empty bucket. So you have to skip over empty buckets to reach to the next non-empty bucket, and then in the next non-empty bucket you have to point to the first node of that bucket. Here is an example, is a schematical view of how to iterate over a hash table. The iterator should keep track of two things. One is the index of the bucket that the element that iterator is pointing to is located in, and second, it has to keep a pointer to the node inside a bucket. So let's assume that you have a hash table implemented in this bucket list, and for example buckets 0, 1, and 2 are empty. Bucket 3 consists of a linked list to 2 nodes, and then bucket 4 and 5 are empty. Bucket 6 points to a node which is a linked list with only 1 element. So the iterator points to one of the nodes in one of the buckets. The current points to the node, and bucket index is 3 because that node is in the bucket number 3. If you call the next element in the iterator, if you call the next method of iterator, then it should point to this node. Why? Because it has to skip these 2 buckets because they're empty, and then in the bucket number 6 it should point to the first node of the linked list. So here is an example of the implementation of the next method of an iterator that iterates over a hash table. Let's assume that the hash table is stored in an array called bucket, and you can access to the cell of that bucket to the bucket at index bucket index by writing this expression, buckets in brackets bucket index. So let's see how the code of next method in the iterator looks like. If current is a pointer that points to the current element that the iterator iterates. If current is not equal to null and current.next is not equal to null, then set current equals set current equal to current.next. What does this if means? This if means that the current points to a element in a bucket, element in the linked list of a bucket whose next element is not null, which means that we are pointing at the middle of a node chain. Then it's very simple for advancing the iterator. All you need to say is current is equal to current.next. Otherwise, you have to move to the next non-empty bucket. How can you move to the next non-empty bucket? In a while loop, you have to say while the current is equal to null, while we haven't reached to the non-empty bucket, you have to do the following. You have to increment the bucket index, and you have to check whether bucket index is still valid or not, which means it is less than bucket.length or not. If it's equal to the bucket.length, it means that we have reached to the end of the bucket list, so you have to throw no such element exception. But if the bucket index is still valid and is still in this bound of the list of bucket list, then you have to set current equal to the beginning of the bucket of index bucket list, which has just been incremented. So current points to the next bucket, and then in this while loop we check whether that current is null or not. If it is null, it means that the bucket is empty, so you have to increment the bucket index again, and do it all the way until you reach a non-empty bucket. And then after you reach that non-empty bucket, you have to point to the beginning of that node chain existing in that bucket that you reached. In the following slides, you can see the detailed explanation and detailed implementation of a hash set in Java that contains an array of nodes, which we call it buckets. So this array will contain all the buckets, and each bucket will be a linked list, but initially that linked list would be empty and would contain only one node. But it gradually get filled up by different elements, and also it has a private integer current size, which shows the number of elements in the bucket, which should be initialized to 0, and then buckets should be initialized to an array of node with length bucket length, and that bucket length should be the explicit parameter of the hash set constructor. So in this slide, you can see the search algorithm for the hash set. This is the same exact thing that we mentioned before, but a detailed implementation in Java. Then we have the add method that you see how it works, and how we first calculate the hash code, and we compress the hash code, and then we check whether the node that we are going to add exists or not in the set. If it doesn't exist already, then we add it to the appropriate bucket. And this is the code for a remove algorithm. Similar steps that we have mentioned in the previous slide, but this is a detailed implementation. And finally, we have the iterator method that gives an iterator through the hash table, and then through the hash set, and then we have the method size, which returns the current size, and the inner class node, which contains the data and a next reference. Also, you can see the implementation of HashSet iterator, which implements the iterator interface. You see that the HashSet iterator should keep track of the bucket index that it points to, and the node that it points to, the node current, and it has a constructor which initializes the private fields, and then the hasNext method, which returns true if there is more than there are more elements in the hash table. Also, it has the next method that we explained its implementation in detail in the previous slides. Then we have remove method, and then this is an example that demonstrates how the HashSet class can be used for different applications. Here you see in the main method that we create a hash set, we call it names. That hash set would have a bucket of it has like 101 buckets, and then we create we add a bunch of strings to that hash set, and then we create an iterator over that hash set, and then we start iterating through all the names, and we print them out. Finally, you can see the output of the program that we have seen in the previous slide. The output of the program prints out the elements that are that were added in the set, but they were not removed from the set. So that's the outcome of the program.